We are now going to study kernel methods that improve upon histograms. Among kernel methods is the very simple sliding window estimate, which corresponds to equation 33. As for histograms, this estimate is also a piecewise constant estimate. However, here we remove the notion of origin. Indeed, here you count the number of points in the dataset that belong to the interval of size h centered at x, the point in which you want to estimate the density, hence the name sliding window estimate. Another way to write this estimate is equation 34, where we have introduced a weight or a kernel function w. This formulation allows us to consider more generic kernel estimates by simply changing the kernel function w. Since we are going to call the function a kernel, we have replaced w by k, standing for the kernel function. Usually, the kernel function satisfies the following conditions. K must be positive, symmetric, and its integral must be equal to 1. Several examples are listed below, but the list is of course not exhaustive. You can find in this list the very classical Gaussian kernel, which is related to the Gaussian density. The rectangular kernel we have seen in the previous slide, which is constant around x and 0 otherwise. The triangular kernel, which has a triangular form around x and is equal to 0 otherwise, and some more complicated kernel, which has a quadratic form around x. Kernel estimates offer more flexibility than histograms, but they are also more complicated to interpret because, when using a Gaussian kernel, every point in the dataset has an influence on the density at each point, which was not the case for histograms, where points were used only for the density estimation inside a given bin. Both methods, histograms and kernel estimates, belong to the class of local averaging estimates, because the estimation of the density is nothing but a weighted sum of the contribution of each point in the overall density. The only thing that differs between histograms and kernels is the way to weight the points of the dataset. An important property of kernels is the fact that the smoothness of the estimate f hat is the same as that of the kernel k, which is used. If k is p times continuously differentiable, then f hat is p times continuously differentiable too. Thus, you can obtain an estimate which is smooth enough if you choose correctly the smoothness of the kernel k. It is not the case for histogram estimates, which are discontinuous. Now we're going to establish a theorem about kernel methods. Consider a kernel which satisfies the following assumptions. The integral of k is equal to 1. K is symmetric. Plus, you have these two conditions on the integrals of the absolute value of k and k squared. Assume also that f is a twice differentiable function such that the infinite norm of f and the infinite norm of f second exist. Here is an exercise. Can you find the rate of convergence of a kernel estimate satisfying the previous conditions, as we have established it for histograms? You can take some time and pause the video. As in the previous upper bound, we're going to find upper bounds for the bias and the variance. Combining them will lead us to the result. First, we focus on the bias term. The expectation of the estimate is given in equation 37. By definition of the integral, since x has a density f, and by doing a change of variables, we obtain equation 39. Then we can use the Taylor expansion of order 2 on f, which is twice differentiable by assumption, to obtain equation 41, where eta u is a point between x and x plus uh. Since we have imposed that the integral of k is equal to 1 and that k is symmetric, the first term in 41 is equal to fx and the second term is null. Therefore, the bias, which is given by the difference between the expectation of the estimate and the target, can be written in equation 42. Rearranging the terms leads to inequality 44, where the integral exists by assumption. Now we compute the variance. By definition, the variance is given by equation 45. Using the independence of xi and the fact that the variance is upper bounded by the expectation of the square variable, we obtain inequality 47. Then we can use the density of x to transform the expectation into an integral. Doing a change of variables and bounding above the density in infinite norm leads to inequality 50. The mean integrated squared error of the kernel estimate is upper bounded by the square of the bias term plus the variance term, as in the case of histograms. You can prove it again if you are not sure of this result. Letting C1 and C2 be the corresponding constants, we can minimize the upper bound in H. This yields H optimal equal to some constant times n power minus 1/5. Injecting this into inequality 52 leads to a mice of order n power minus 4/5. The rate of convergence here is not the same as for histograms. It is faster, and one can show that the rate obtained for kernel estimates in the case of twice differentiable function is optimal. This means that we cannot find an estimate with a faster rate of convergence for all twice differentiable functions. It does not mean that empirically, kernel estimators are always better than histograms. But if you had to choose only one of the two classes of estimators, you should probably choose kernel estimators, as they are able to estimate more efficiently some densities. If we had looked at densities that are continuously differentiable only, we would have noticed that histograms and kernel methods both achieve optimal rates of convergence. The fact that kernels are theoretically better than histograms comes from the regularity of the density, here twice continuously differentiable. As for histograms, we have found a way to choose the parameter h. However, in practice, you may prefer to use a cross-validation strategy, since knowing the constant C1 and C2 is often impossible.